Let's go ahead and take a look at Overflow 5, the final challenge of the PicoCTF 2013 binaries. So first thing we're going to do is we're not going to bother executing this one. We're just going to jump right into Binja. And my alias only works if you don't start with a space. There we go. And we will open up Overflow 5. And we're going to take a look at two things. First off, the main function we can see is more or less identical to the main function in binary number 4. And if we look at the vuln function, we can see that once again, we don't have any conditional branches or anything like that. There's no code in here that drops a shell. So one might think, okay, we just need to put some shell code on to the stack and then overwrite the return address, jump into that shell code. But unfortunately, that will not work with this one either. And I'm going to show you why. We'll use the readelf utility for reading binary files, #l for the headers, and then we'll go overflow 4, and we'll look for the stack segment, and there we go. That's the information about the binary stack. So now we'll do that for overflow 5. All right, there we go. And you may notice that there is a difference between these two. Notably, the permissions on the stack for overflow 4 are read, write, and execute, which allows us to run code on there. But the permissions for overflow 5 are only read and write, which means that if we try to jump to the stack, we will get a segmentation fault because that is not a segment that we are allowed to execute. So what we'll have to do instead is called a return to libc attack. And I will include a link to a decent write-up on return to libc in the description of this video. We will just jump right in, and you can read the description if you are not quite familiar with how that attack itself is performed. First thing we're going to do now is enable dynamic analysis tools, of course. And now we're going to fire up GDB, and we're just going to run this program. No inputs or anything, because we're not too concerned with what's on the stack right now. What I'm looking for is the address of the system function in libc. So now that we've got that, we're going to go ahead and fire up Vim here and create ourselves a Python file in which we're going to write our exploit, and we're going to store system, if I could spell, OXF7 E4 8D A0. There we go, system address. Okay, so now that we've got that, that is going to get us started here. So system, as you may have guessed, is a libc function that will read a program string off the stack and then execute that as a command. So if we run system/bin/sh, we will end up getting a shell, ideally. And one thing we're also going to go ahead and do is we're going to open /lib32/libc.so, and this is where system actually lives. So we're going to go over to the function viewer here, find the system symbol, and we're going to keep that open just for safekeeping. Might have to go back to it later just to help out with some things. So now let's go ahead and kill this binary. And let's find our memory viewer here. Now, rather than waste another iteration on this, I'm going to point out right away that vuln does not set up or tear down a stack frame in the course of its execution. We see that it subtracts, here if I think that's 1056, yeah, or 1052. Yeah, it subtracts 1052 bytes from ESP and then adds 1052 bytes back on ESP at the end. So it does create some stack space in order to hold variables, but it does not touch EBP at all. It doesn't run the leave instruction, doesn't set up a stack frame at the beginning, which means that the return address parsing in our traceback viewer won't work because it looks at an offset from the base pointer, but that's not something we're tremendously interested in right now. What we do want to know, if we go into main, and we are not currently running this, I think. So let's just give it a little bit of data to play with. Let's fill up the, say, 1024. I'm guessing 1052 bytes is a 1024 byte buffer plus some other stuff. So we'll give that, run this, go into Vuln, and we will set our breakpoint right at the beginning. Yep, breakpoint set, and we're going to jump into there. All right, so now what you'll notice is that we subtract ESP here, but then none of the other instructions in this function have ESP as the destination other than the add instruction. And that add instruction is just going to bring it back to the same place it was. So when we get to the return instruction, when you take a look at that, as you'll recall from looking at the LLIL, what return does is it pops an address off the stack and then jumps there. So where ESP is now is effectively going to become our return address once we get to the end of this function. And I'm going to go ahead and highlight that so we don't forget it. That is, if I can get the highlights to work. There we go. Okay, so we'll step over that. And now you can see it's allocated a ton of space, and the highlight has also moved with it because the highlights are at relative offsets, not absolute, which is going to make us lose our place, unfortunately. But, whoops, there we go. There's too much data in the memory viewer right now. It's running a little bit slowly. And it certainly doesn't help that I'm recording the screen. Jump, jump. I'm going to jump over this call to stir copy, which is going to fill our stack with A's. And then we're going to add a bunch more to ESP. And we can see it's back where it was before. And the value contained there, if we go over to the register viewer, switch to dereference, and then look at ESP, it points to OX 8048.405, which is the address of main plus 69. 4405, which is going to be this instruction right here. Yeah, so that is the return address as we expected. Now let's see, we gave it 1024 bytes. It looks like we are 12 bytes short of actually hitting the memory, the return address from where we are. And in fact, we can double check that. So 1024 plus 12 should be 1036. And now if we see, let's switch over to medium level IL here and go ahead and rename these. So stir copy is dest source. Call that dest source. And then this address the address of variable 40C is what desc gets set to, so we'll call that, we will attempt to call that, oh boy, there we go. We'll call that buffer. And now if we go into, actually let's go to the low level IL, just to make it a little bit more clear. We can see that buffer over here is ESP plus 10. Oh, no, sorry, not ESP plus 10, ESP plus hex 10, which is 16, of course, and 1052 minus 16 is also 1036. So we know that we have to go 1036 bytes in order to overwrite the return address. So we'll go ahead and mark that 1036 bytes. Okay, so that's good. Now, we're going to need to figure out how to get system to execute with the proper arguments. Oops, already in insert mode. Okay, so we'll say exploit equals, let's define a NOP just for the heck of it. Back x90. Wait, sorry, we don't actually have to use, it's fine. We don't actually have to use NOP there. Since we can't execute anything on the stack, it doesn't make a ton of sense to use NOP. Unfortunately, it's just kind of force of habit. Tell you what, let's make it A, just so that, and we'll change the name to stub, just so that we don't get confused after the fact. Yeah. Stub times buffer length plus struct.pack system, oops, that needs to be I, and system address, which we spelled as ADDR. There we go. And hopefully that runs as expected. Okay, I finally fixed my many syntax errors. So now we've got all of this base 64 encoded here. Most of this is just A repeating over and over. But you can see the pattern changes a little bit at the end when we have the base 64 encoded address of system there. Okay, so let's go back into here. And we'll go ahead and kill this because we don't need it anymore. Now we will set some new arguments. Go to base 64 encoding, paste that in, run it. It'll hit the breakpoint at main. You can see down there. Going to jump to the breakpoint in Vuln. Give it a second to update. Now let's start stepping through. Let's get all the way at the top so we can see the fireworks. There we go. And here's our call to stir copy. So let's scroll back down. Just take a quick look. The return address is going to be right there, offset 32 bytes from what we think it is. That'll take us back into main. And now if we jump over the call to stir copy, our return address is now changed to the address of system. Excellent. That is exactly what we wanted. Of course, there's an asterisk attached to that because we're going to call system without really knowing what it's going to do. Okay, so let's go ahead and jump to the return statement there. Now let's take a look at some of our other windows. We can see that we're executing system. We can see what our current address is, the traceback in the viewer. But we don't really have much other guidance, do we? What it would be nice to know is to have the proper instruction highlighting on the other binary ninja view, but unfortunately, I think I may have noted this in one of the previous videos, but Binary Ninja doesn't really have a good way to sync up two different binary views right now, so while it would be nice to have the highlights carry over from this view into libc, we don't actually have that option, especially given the fact that libc lives in this program's memory, and the addresses you see here are actually just offsets. Like for instance, the current instruction pointer is F7E stuff, whereas the system function is at an offset that starts with 2 zeros in libc. So we can kind of keep track of what's going on, but we're going to have to be pretty careful to keep an eye on it without actually having the disassembly. What we'll have to do is go ahead and look up the documentation for system, which I had this open before and then foolishly closed it. But so we can see that the argument system expects is a chart pointer to the command that it's supposed to execute. So what it will look for is it will look for wherever ESP is pointing when it first executes. Then it will look for then it will skip over the 4 bytes after that, and then it will look for the pointer that is supposed to be its argument, as according to the calling conventions. So what we'll do is we will first add a dozen bytes onto our exploit so that we fill out that length properly, and then that will let us calculate the addresses of where our that will let us figure out the address of where our string of bin/sh is supposed to be. So let's go back into our file here. And I suppose it won't actually be a dozen bytes exactly. It'll be a little bit more than that, because bin/sh is not 4 bytes. So we'll go ahead and define our command there, which is bin/sh. And then we'll go ahead and we'll start messing with our exploit here. So we'll add on just 4 empty bytes to fill up that spot, and then struct.pack, and then this will be the pointer to our command. We'll call that command pointer, and then we want to add on the command itself. Alright, so now all we have to do is, well, first we have to create the actual command pointer, and we'll fill that up with junk for now. And then all we need to do is figure out the address of where that command is going to be, and everything should be fine, because the length of this is not going to change in between. So we'll go base64 encode that. You can see we've got a little bit more stuff appended at the end there. Go back into GDB, kill the program, set the new argument. Lots of the same thing. There we go. Run this, jump into Vuln. Oops, okay. So what we're seeing here is that GDB is complaining that something has gone wrong inside, which happens on occasion. So we are going to close all the windows here. What did I? Yes, I would like to save that. Alright, there we go. We're now back in business. So we're going to go ahead and set the argument to GDB. paste that in. Then we're going to go ahead and run it, and we'll print up. Here's the beginning. To restore our breakpoint. Boom. Continue there. And let's start taking a look at this. Okay, jump over to call the start copy. We've got lots and lots of A's. And we can now see there's the address of system. There's our 4 stub bytes. There's what's going to be the address of our command string. And there's the command string itself. And you can see that the semicolon actually got stripped off of there, but since it's followed up by a null byte, we're not going to worry about it. In fact, stir copy should have probably put that null byte there, I expect. So we'll take a look at our address, and that is going to be my other tab. There we go. For our vim. And pointer is going to be FFFF D1, and then we're 8 bytes ahead of where that line actually starts from the look of it, so 0, 8. There we are going to WQ that, base 64, copy that, go to GDB, kill the program, and here we go. Hit OK. So now we're going to start that over again. Continue to roll. Jump all the way over stir copy. There we go. Okay. So now, let's go one more time just to make sure that our return address is still where we expect it to be. And yep, we've got the address of system there. Got our filler bytes. And then FFFFD108. Okay, that looks good. And now, let's go ahead, delete all of our breakpoints. Yeah, so we'll return into system, and now it'll look, our stack pointer is pointing there, so it'll look here for its first argument, and it'll find the pointer to our command string. Now let's hit continue, see what happens, and look at that. We've got a shell.